Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Jay Gallagher with us today. Hello, Jay.
Hello, Frank. How is life in Phoenix? Are you guys roasting yet?
We're actually getting fairly cool in the morning. We were down like in the 70 Fs or something this morning, but we still heat up pretty good in the afternoon. So we'll still get up to about 109 today on this September 27th of 2024, post-equinox as we go through. Uh,
Yeah,
and Jay, where are you located at?
I am located currently in Bloomington, Minnesota,
Bloomington.
where we are roasting at night at 59 degrees.
Ooh.
And the days are getting up into numbers that start with 8, which is unbelievably hot. Mosquitoes are crawling out of the air in shock.
Well, in Phoenix, when it goes below 100, people start pulling out their winter gear that,
That's
is
right.
completely unacclimated to anything. So, yeah, very
Yeah,
cool.
when I lived in Tucson, they talked about ice melting on the Santa Cruz when it hit 100.
Absolutely. Yeah, and I spent a decade in Chicago too, so I'm a little familiar with those Midwest winter seasons.
Yeah, it's coming.
Yeah, very cool. So as fall actually started in Bloomington, are we getting a little color on the trees?
Not yet, not yet. We are
Getting
still warm, and we can definitely see that things have changed a bit in terms of seasons compared to when I was here in the 1970s.
cool. Very nice. And Jay, what do you like to do for research?
Well, I've always been very interested in mainly in how galaxies evolve and how star formation and stellar populations feed into galaxies. This, of course, leads me down many side paths, for example, into understanding massive stars and how they evolve on
Yep.
one side. And the other side on feedback is because I was at Wisconsin for quite a while, is neutrino astrophysics, which is
Ooh,
a diagnostic of what's going on. But
ooh,
that's not the topic today.
that's
But
not the topic today,
they're all
but
connected.
we should talk about that. I'm interested in that one. Very cool. And that is going to bring us to this super awesome APJ supplement article. It is open access. It's the open access era, people. You can go get a copy for free. Go get one.
Indeed.
An imaging and spectroscopic exploration of the dusty, compact, obscure nucleus galaxy, Zwicky 049.057. And Jay, take us away.
Okay. Well, as you can see, this is a team effort. And the team involves my colleague, Ralph Catula, who I work with on this at University of Wisconsin, Lauren Laufman, and Emily Geist, two former undergraduate
Hmm,
students, Suzanne Alto, who is at the Chalmers University and is a leader of the team. There are several Chalmers people there, Nick
hmm,
Falstad, Sabina Koenig, Jalen Krause, also a former Wisconsin undergraduate,
very
George
cool.
Pribben, who is at NRAO in Florida, Claire
Hmm,
Withers, who is a postdoc at Chalmers in Sweden, Aaron Evans, who is one of the pioneers in this area, who
yes.
is at UVA and NRAO,
Hmm,
and Mark Gorski, who is currently a postdoc at Northwestern University.
great
So
shout out. Great
I
shout
should
out.
put this into context because here we are studying in, I would say, exquisite detail. Many readers would say over detail. And uh, why are these galaxies interesting? So let me jump back in time a little bit, if you don't mind. Okay.
Yes, please. Please do.
Alrighty. So basically, uh, once in the sort of early phases of understanding dust, dust was studied in absorption, which is what we do here.
Yep.
And essentially, what we're looking at is why are these galaxies discovered only now? Why are we busy looking at them? And why are they rare? That's if they're rare, you need to study the individuals, thus Vicky 49.
Yes.
And the key to these galaxies is that they have nuclei that are buried under very extreme dust layers.
Okay.
And these hidden nuclei we call cons for compact obscured nuclei. And the
Mhm.
team Susan Alto put together is the Conquest team.
Okay.
Now, it was
Quest.
recognized probably first with X-rays that some active nuclei are hidden away. Those show up as the Compton-thick nuclei.
Yep.
And then later on, as infrared came into play, really 40 years ago approximately, the ultraluminous infrared galaxies and luminous infrared galaxies appeared.
Mm-hmm.
And with those, there became the issues of, okay, where is the power coming from?
Yeah.
I remember at that time, everybody thought it was a big starburst, maybe kiloparsecs across. A blown up version of M82 was what
Okay.
we had in mind.
Okay.
But as resolution improved and techniques improved, it turned out that a lot of the power is coming from the very central few hundred parsecs.
Okay.
And how do we manage to miss this? Well, first of all, we didn't have the resolution. And secondly, it turns out that in some of these systems, such as ARP 220, the nuclei are so compact that you need really sub-arc second resolution to find them.
Yes.
It was only when things like ALMA appeared, high resolution work with HST, and other radio interferometers that we began to explore these systems and discovered that there are a group of galaxies at the end of sort of the sequence of how dense can you make the center.
Yeah.
And these are the compact obscured nuclei.
Mm-hmm.
So
Cool.
Zwicky 49 was one of the early members of this group. It was found by Zwicky, amazingly, on a 16-inch Schmidt telescope, found this little galaxy that looked pretty sharp, which is strange because it's very dusty, and this was a blue plate. And following that, it rested for a while until Martin in France noticed that it was a dusty galaxy, that it was reddened across the minor dust lane.
Mhm.
There it again stayed basically until the HST data came along. Nick Scoville used NICMOS
Yeah.
and noticed that this had a very strange set of dust patterns.
Mm.
Later followed by Almudena Alonso Herrero, who also has worked a lot on this galaxy.
Cool.
So with this, the picture began to develop that this was a galaxy that had a central starburst, that it basically had mission lines, and that it was a luminous infrared galaxy.
LINRD.
So, any other peculiarities? Early on, it also joined a very elite group of galaxies where the neutral hydrogen 21 centimeter line, instead of being seen in emission with a big beam, was seen in absorption with the big beam. A narrow, broad absorption with a narrow peak. So, what was this going on? That also just got put into the literature, which is why we're there.
Mm-hmm.
Then,
a lot of wavelengths.
a lot of wavelengths, right. So this is a multi-wavelength business to get at this. So we still haven't gotten to the con. We've gotten to the fact that it's an infrared luminous galaxy. It's got gas in it. Molecular line observations began to show there was a lot of molecular gas and it was centrally concentrated. How centrally concentrated only became clear as ALMA got onto the scene. And it became obvious that the central gas concentration goes all the way down to the sub 100 parsec scale to sizes like 30 parsecs.
Wow. Cool.
So these nuclei are really deeply hidden. And again, the key to finding them was you had to be able to resolve them, which meant you needed sub-arc second millimeter observations to do it.
Right.
Okay. Then the problem comes. If you look at the radio continuum, which we discussed later in the paper, you can find out where the power is coming through the dust, because the L-band continuum doesn't care about dust.
Mm.
So what you find out is that basically 85% of the continuum is also coming from this nucleus. So not only is the nucleus compact, but it's powering the whole works.
Wow.
So it's a hidden power source sitting inside the galaxy, producing on the order of 10 to the 11th solar luminosities inside of 30 parsecs. Okay, if you're an astronomer, you immediately say, okay, how does something like this work?
Indeed.
And how could it be fooling us? Because in cases where we don't have high angular resolution, such as at high redshifts, these things could be lurking around and be difficult to tell for sure that it's there.
Right.
So detailed studies come into play.
Nice.
This paper is part of a series of studies carried out by the Conquest group to look at different aspects of the nearby prime examples, of which Zwicky 49 is one. And I'll talk a little bit later in the paper about some of the other work on this galaxy and try to put it in the context of what's going on. Okay, goals. Why look at an infrared bright galaxy in the optical with HST? The answer is, if you want to detect gas in the region where it's transitioning between neutral hydrogen and molecular gas, you have to look, and it's occurring on small scales, which we think is the case in this galaxy, you need high resolution. Well, in H1 emission, you simply can't get to the sub-arc second resolution. Right now, you can get to sub-arc second resolution in infrared emission at 10 and 20 microns of JWST, but that only samples the gas that's very near a warm radiation source. So if you want to look at the more general question of feedback, which is what I'm interested in, how does this little tiny nucleus connect to its giant galaxy? How is this working? You need to be able to trace this dusty gas as it flows through the system. The way that we decided to do this was to look at absorption.
Yeah.
Dust absorption can be observed with high resolution with HST, which gets down to a 20 parsec scale. So this is a very classical approach. It's work that was developed as a concept really in the 1950s, but it's applied in a new way with Hubble because we can get the resolution that we need to follow the dust in this galaxy and also see what else shows up.
Yeah.
Okay, let's go ahead. So we observed this with Hubble Space Telescope with the Wide Field Camera 3 imager, and we observed it basically in the HST U, V, I, and H bands.
Okay.
So this was part of a program where I was the PI, and it was another team effort to get this kind of thing. So this is a product of HST. So here we go. A little prop, remind everybody this is a good thing.
That's awesome. Very good.
Oh yeah, by the way, during these observations, the HST was obscured. Okay.
Very, very good.
So using HST, we did get images of this galaxy. And if we go to the figure below, this shows, let's stay with the top for the first. You can see that there is a oval region, which is a disk. On the left is a ground-based image from the NOAO IR Lab Explore image. You can see the dust region that Martin found in 1988. Yes. The HST color image shows you how dust pervades the central part of the galaxy. There's diffuse dust. There's an outer, somewhat bluer disk that isn't very blue. It's sort of neutral color. And there are distinctive V's that I call pillars, which were discovered by Scoville et al.
Scoville, yeah.
In addition to that, there are dust arcs and dust clouds extending out of the disk, which fits with the idea that this is a violent starburst. I'd also call your attention to the dust lane crossing on the upper left, near where the upper line joins on the center picture, right in there. That is a polar dust lane. And that's telling us something we didn't know about this galaxy. It's thought to be single and isolated, but it's not. Okay, let's go down for a minute.
Cool. I think that's a discovery on this paper too.
Yes. Oh, by the way, one other thing, the little circle on the right side, important thing, shows you where the pond is located. Right there. Only we don't see it. It's in the middle of this bright arc, and we'll talk a little bit about that later. Why is something that's hidden in a bright location? It's physics.
Yay.
Okay, the 555W figure shows rather nicely the polar dust lane. You can see one on the upper left, and you see a little bit of it on the bottom right as well. So this galaxy, any galaxy with a polar dust lane, has visited its friends. As you go up in wavelength, the dust becomes transparent, and what's left behind that you can see is you can see the brightest plume sticking out of the center that originates from above the con. And you can, that one, the one on, it's over there, And the V tends to vanish. The other one is actually there, but harder to see because it's narrower. So, and if we go all the way to the left is an important point too to keep in mind, which is the little bit of diffuse dust has been done a very nice job of making most of the galaxy disappear. If you can get the dust puffed up out of a disk, you can obscure a galaxy with remarkably little material. People who live in Phoenix know about this. Big wind, dust comes in, pretty soon you can't see your neighbors.
Oh, our monsoons are infamous, yes.
Yeah, so it's a matter of getting the dust up and into suspension for hiding galaxies. And that's another interesting aspect of this system. All right, let's proceed onward with the paper a little bit.
Okay.
Okay, we can go down. So I'm not going to go, let's stop there. We did not do a detailed study of the stellar body, but we found also something interesting. Those of you who are into galaxies can see on the left how the outer part of the galaxy follows a straight line in terms of surface brightness versus radius. This is characteristic of exponential disks of galaxies. Galaxies are well known to have exponential disks. It's less well known how this occurs. There's still a lot of discussion of this point, but it says there's a disk. Also, you can see how the brightness drops below the extended outer region in the center. That's the dust absorption and action eating out of the galaxy.
Yes.
That's the disk part. On the right are isophotes, and you can see the oval isophotes in the center of the disk, and then in the outer part they become circular. This was also not previously known, and this kind of circularity could be understood if there was a halo, but if you notice the isophotes kind of jam up around the edge of the disk, And this is what you get when you get a warp. So you get something like this,
Ah, yeah.
something like that. So
Right.
this is also a hint of a past interaction. It is most likely, but not proven, that the galaxy is warped.
Okay. Very
And
good.
that outer disk is very diffuse and has a much longer scale length than the inner disk. Its colors are moderate but not well measured yet. All right, now that we know our galaxy, so Zwicky 49 is not a nice, well-behaved galaxy. It has excess dust, it has an outer warp, and it's got a polar ring.
How exciting. Okay.
Okay, let's go ahead. Normally, we would expect a galaxy like this to be in a group somewhere.
Yeah.
We can go past the disk here, go a little further down.
Okay. Yeah, structure of stellar bodies.
We'll talk about the spectra later, so we'll
Okay,
get
the
to
disk.
that.
And we got photometry.
Okay, there, just stop there and go back up a little bit.
Sure.
Okay, so we did photometry and we found that it's fairly compact, which by the way agrees with Zwicky. So using a multi-billion instrument, we have managed to confirm one of the major results from a 16-inch Schmidt with a used photographic plate. But
Big.
we've found a lot more as well.
Go wrong.
So essentially, the question is, what about the environment? Where did this come from? It turns out that this galaxy has only nearby neighbors who are not very bright and are fairly distant.
Okay.
So this isn't the typical case where you find a rich environment and the galaxies have hit each other.
Mm-hmm.
One of my students studied a galaxy in a similar situation and decided this was an example of a galaxy becoming, as she put it, this was Leah Fulmer, a galaxy becoming isolation via annexation. It ate its neighbor, so now it's isolated.
There we
And
go.
49 seems to be one of those. It once had a companion, it
Oh,
now
wow.
has none, so it's in catalogs of isolated galaxies. It shows
Okay.
you one has to be careful. So even though this galaxy is living definitely in the local universe slow lane, low density environment, dwarf companions, not much around, it still is undergoing rapid evolution in a specific phase.
Nice.
Okay, let's proceed.
Cool. Very good. Okay. Good. All right. I'm with you.
Maybe a lot of details there. There's a list, if you like them, of the companions. Anybody who'd like to go out and get spectra of them and learn a bit more about them, that would be great.
We'll come back to
One of
that.
them is not detected in H1. It'd be more interesting to know what's going on there.
Okay.
Okay, from there, we move from structure into the colors of the galaxy.
Okay.
And we undertook both two ways of looking at the structure, small scale structure. We spatially filtered the galaxy, which is to show the bright regions. So in this case, by spatially filtering, I spatially filter my hand, and I end up with my thumb sticking out because it's the high frequency.
Okay.
So now you can see the pillars more clearly. And we also made color maps, which are down below. And the color maps show that the center of the galaxy, darker is, in the right side is more dust, is just totally obscured by dust. And the
Yeah.
dense dust is, no surprise, concentrated into specific regions. And these are interesting to me and to our team because these can trace the feedback from this con that's hitting in the center, producing most of the power in the galaxy.
Yeah.
But what's interesting is we don't see obvious things pointing at the con other than the first pillar one dust lane.
Yeah.
Power source there. To do that exactly in the upper one, Frank, you can see it. And below that, it looks just like a starburst. Okay, let's proceed on a little bit further.
One question. What is
Sure.
the circle here in the lower right? What is
Oh,
it?
I'm sorry. That is a comparison field of the outer region. The way we map the dust is both, I should go back here and explain this,
Okay.
is both an intensity change and color change.
Ah, okay.
Because dust reddens, you can measure the color change. The problem is to do that, you have to know what the color of the underlying population is ahead of time.
Yeah.
The answer is we don't really know. We don't have good enough data yet. It's coming. But what we did in this case was to take the outer disk as the unreddened color.
Okay.
And we know the outer disk, if anything, is going to be redder than a star-forming region in intrinsic color.
Hmm.
So therefore, we underestimate the amount of dust by doing this in terms of the color change. So that is a comparison region. And in the outer disk, by the way, the colors are very uniform.
Okay. Nice.
Okay, and also the structure of the outer disk is uniform. We don't see much in the way of arms or anything else, or a few dust patches, but that's about it. By the way, the outlined region is the region where we measured the dust mass, the actually gas mass. We converted into
Oh, on
opacity.
scale here? Yeah, yeah. Okay.
We're going to come into that in a minute.
Okay. Very good.
There
Thank
you
you.
can see the polar dust lane is also reddening things in the right picture.
Yes.
Okay, so now we have our galaxy. We have a disk galaxy. We've got a lot going on in the center with a lot of gas. We have dust lanes sticking out of the plane.
Yep.
And we have sitting in the center, the size of literally the top of a pinhead, a nucleus that's powering the whole works.
Wow.
Okay, let's proceed. So how does this galaxy, so now the question is, how is this galaxy operating?
Okay, that's a good question.
Okay, so one of the first things we did is we asked, okay, what's the structure of these distinctive dust features? And on the right, you see a diagram that was put together actually by Lauren Laufman as part of her undergraduate work.
Nice.
And we took little regions. Actually, the pillars consist of little clumps of material, and we measured the dust opacity in each of those regions.
Okay.
We also looked at some clouds and some dust arcs. Now, the way you measure an opacity is you measure the brightness of the light in a given band relative to a background. To do the background on the left side, what we did is we inverted the galaxy, and we subtracted the back of the galaxy from the front of the galaxy. And the back is less dusty because it sticks out of the plane. And so in this way, we get the contrast of the distinct features just by removing the background. We made a very simple model. You have to be careful about dust and absorption. If I were to move that dust lane, would you move it, Frank? Oh, it doesn't move. Okay.
What would you like? Move what?
In the lower figure, there's a region called dust. If that were in the back of the galaxy,
Yeah.
right, I wouldn't see it. I would just see the stars in front of it.
Okay, I'm with you.
If I move it a little bit out of the back, I'll get a little bit of dimming. And in fact, if it's opaque, I would get no change in color whatsoever, just a change in brightness.
Yes.
So by comparing the change in brightness to the change in color, you can determine the optical depth of the dust.
Cool.
And this is a technique that Bill Keel has used in the past, and that Deidre Hunter and I did some pioneering work on using a TV-based imager back in the 1980s.
Very cool.
At about a signal to noise of 2, but we managed it. So this is the way we measure the dust opacity. We then estimate a gas mass by going from a dust optical depth to a gas column. That amounts to selecting a gas to dust mass ratio. So we're not independently determining the dust mass here. We're making a ratio. Okay, let's go ahead.
Okay, I am with you. Very good.
Okay, so these are the, in the section 4, we go through the different kind of dust features, which I've already outlined.
Yep.
And in addition, I should add point 6. If you look at these in more detail than you'll see on the TV, you'll see faint dust lanes extending on the opposite side from the pillars, but they appear to go towards a point, and they're a bit puzzling. Well, recent reduced observations with SALT show that there is a ionized outflow on that side of the galaxy.
Oh.
So probably something's happening on the back side of the galaxy, but since we're looking through the system, we don't see it very clearly.
Okay.
The details are not clear, and they're not explored in this paper.
Okay. We will come back to that. Okay.
Okay, now into the dust quantification. Here I'm following results that many other people have used. The problem is that the simplest model for dust is to assume that the dust is in a screen in front of your source.
Yes.
That gives you a minimum dust opacity. That's called the foreground screen model. Our embedded cloud model is the next step, but you can only really do that on localized regions like the dust pillars, where you could argue there's a cloud sitting in some medium. If it's a diffuse medium, it doesn't work. One more thing to keep in mind is that if I make a mixture of dust and gas and stars, mix them together, it's not going to be dark. Radiative transfer tells you that an optically thick object approaches a brightness set by the source function, which is the ratio of energy input to opacity.
Yes.
So dusty regions with a lot of stars in them do not necessarily appear as dark.
Okay.
Dark regions have a deficit of internal energy. So be aware of that as well in interpreting the data. Okay, so what did we do then? We used a foreground screen to do that big dusty region in the center.
Yes.
And we got out a gas mass that was really a few times 10 to the 8 solar, or order 10 to the 8 solar masses or so.
Okay.
And we called this the extraplanar gas. The number is 2 times 10 to the 8th, but that's actually a lower bound because we used a foreground screen there. Right. And there are several approximations. It's a very rough number, but it tells us that the gas reservoir is substantial. And since H1's not seen in emission, this is one of the few ways we can get at the amount of gas in the reservoir.
Hmm.
That's a minimum amount.
Right.
We did that with the foreground screen. Then we asked this embedded slab model, went down to the specific cases where we can put a gas cloud into the system and say, where is it by measuring color and opacity, and tried to measure the optical depths and thus the amount of gas in those narrow pillars. Now, this is where we really needed HST, right? You cannot resolve those pillars from the ground. The gas columns are too low to detect in CO. So the way to map them is dust absorption. If there were radiation sources inside, you could do them in emission with JPST, but you need to have the dust very warm, and it doesn't seem to be that way. So this was why we chose this very classical kind of approach. It's also why there's a lot of text on how to do this, because there are many assumptions that go into this, and I'd like the reader to be aware that we know there are approximations to understand that these numbers are not super precise, but they give you an idea of what's going on. Okay, so let's go down through a lot of text that's going over that business. Okay, and here's the table where we use this central approach to measure optical depths, and we know it found that some regions were very optically thick, particularly the narrower and less prominent dust lane appears to be optically thicker than the one that's clearer. How is this possible? Well, if you remember, we said the case where there is essentially a change in color that's fairly large, but a small change in intensity means the object's in the back of the system.
Yes.
So these two dust pillars are at different distances with respect to us.
Okay.
The one that stands out is in the foreground. The one that's less pronounced, the other one on the V, is in the background. So they're like that.
Got it.
So
Got it.
that's another nice thing about doing dust absorption in galaxies. You can pull out 3D structures in the sense of different planes, so we can tell where things are with respect to our sight line.
Very nice.
So this is the reason why in this paper anyway, the lead author took the view that this is most likely not a cone seen edge on, because then the two sides should be about the same, but more likely two collimated outflows, or possibly part of a cone and an outflow. So, but this is not settled, but that's the basis for the decision in the paper. If you look at the masses, you'll see that they're not gigantic. That the gas masses are on the order of 10 to the 6th to 10 to the 5th. So not gigantic, but still substantial. So this is interesting because, again, this indicates that there are, is consistent with sort of a collimated outflow. Let's go down a little ways and we'll talk some more about the pillars.
Okay, those are pillars, pillar 1 and pillar 2.
You can go past the, I called them dusty pillars 1 and 2. This is the interesting diagram.
Very cool.
If you look at dusty pillar 1, if you notice right in the middle of that rectangle, the color is the same as the background. Pillar 1 does not have a color change.
Yes, yes, I see it.
So that suggests that it actually is more optically thick than we think, and is basically in the foreground with a few stars in front of it. The other pillar, which is faint in absorption, is better defined in color. And that's what you get with an optically thick object embedded further into the star.
Nice.
And that's why we think we have two different systems here that we're looking at. And again, the round circle is the nucleus right at the base of pillar 1.
Yes.
And the blue streak arm is an arm in the disk where the dust is low. It's not really very blue because there's still a lot of dust, but it shows the intense knots of star formation in the inner disk of the galaxy.
Got it.
Okay, so now we're beginning to get a picture. The nucleus appears to connect to pillar 1. Pillar 2, we'll see later on, does not meet the nucleus. You can see that even just on this picture. And so we may have multiple things going on. And I'll comment on that later. It's consistent with what we're learning about this galaxy. Okay, next up.
Very nice. Okay, I'm with you.
Keep going here. All right.
Salt.
So let's go to the two pillars here. This sort of sounds like archaeology, doesn't it? The two pillars of an ancient world. This is an ancient world here.
Oh, it is.
So essentially, this is a discussion of where do the pillars come from. That's in 4.5.3 on the left side there.
Yep.
Okay. So I just want to give you a heads up here. We don't know. But pillar one is in the general direction of multiple outflows from the nucleus of Zwicky 49. There's a recent paper by Boy-Lankar, just published, that shows the multiple outflows coming from the nucleus on subarc-second scales obtained with high-resolution observations from ALMA. So we know that that's happening. There's also a radio outflow that more or less lines up with pillar one. So pillar one does seem to connect to outflows in the nucleus in very general senses. Pillar two does not and remains a bit of a mystery.
Indeed.
Okay, so let's set aside the pillars and now ask about the disk here. So we explored the disk with SALT. We obtained spectra with the Southern African Large Telescope. This is a major axis long slit spectrum using the Robert Stobie spectrograph.
Very cool.
An additional paper is under preparation by Claire Weathers, who's obtained VLT Muse observations that have the advantage of area spectroscopy and higher angular resolution. SALT, on the other hand, has really good sensitivity to diffuse emission. So what did we see? We saw the strong emission lines in the center of the galaxy that had been observed before with single slits, with blown, with other telescopes. And the difference is that we got kinematic information this time.
Good.
And so we saw the extended emission lines of helium-1, forbidden nitrogen-2, H-alpha, and forbidden sulfur-2.
Okay.
And if we go down here, we can get the answers all in the figures that are coming up. Page.
Yeah, I'm following.
Okay.
Sodium D.
So the lower figure, the bright are emission lines, and you can see the tilted lines of a rotating disk or ring. That's in the nucleus. And you can see how the edge of the lines extend past the absorption. So it looks like the ring is rotating a little faster than the outer stars.
Ooh, okay. Okay.
So how is that possible? The answer could be that the ring is a thinner disk than the stars. If the stars are puffed up a bit, then some of their energy is in dispersion and it rotates more slowly. Okay. So there's a very good chance that these are rotating in the same potential. The offsets are small, so it's also possible that there's a measurement error here. That's always a possibility in astronomy. You can see also in the H-alpha line that once you go beyond the inner roughly kiloparsec of the disk, the stellar light is seen in absorption. And if you go take your arrow down a little bit, you can see the faint emission in the outer regions, just a little bit up a little tiny bit. Go to your left there.
Yeah.
Very faint emission in H-alpha.
Yeah.
And notice how it's moved away from the H-alpha absorption.
Yes.
That emission is sitting at the center velocity of the galaxy, and it's typical of extraplanar ionized gas. Okay, so what do we have? We have a rotating disk.
Right.
We have H-alpha absorption rotating outside of it, but maybe more slowly, possibly due to dispersion. And we have ionized gas probably sitting in a plane above.
Okay.
That's all fine and dandy until you look at the sodium part of the spectrum, and that's the upper part.
Yes.
It covers the same area. The sodium shows no velocity gradient whatsoever. The sodium is sitting at the center of mass velocity of the galaxy, just hanging out there.
Okay.
So how could that be? Well, maybe the sodium is associated with the face-on component that would not show much velocity of rotation. Remember those outer isopods that were around?
Right, right.
So perhaps we have a gas cloud hanging out even further out than we're seeing in absorption. Okay. But mapping this is a bit of a puzzle. I think this might also be a bit of a discovery. I don't know of any other galaxies where the kiloparsec scale sodium is showing no rotational speed at all in an elliptical galaxy, which is definitely a rotating galaxy.
What a curious beast.
Okay, but now think of the following. I want to put something in the nucleus.
Okay.
The nucleus is in the center. Things rotate. Angular momentum is r cross v. So I need really low specific angular momentum to get into the center. Hold out. Here's this sodium sitting out there with no rotation. Low specific angular momentum.
Right.
Maybe we have a reservoir here that can feed the center and really concentrate gas into the middle without hitting the centrifugal barrier in a big way.
Okay.
So these things could connect. And it shows you why you have to take a multiple object approach to dealing with these kinds of weird galaxies.
Very nice.
Okay, if you go down below, I'll just go through this one quickly.
Sure.
Figure. This just shows the rotating disk with some numbers, the scales, the velocities, and you can see the H-alpha absorption and you can see the emission. This explains just what I went through.
Yeah.
Okay, let's proceed onward. So now we have our galaxy, we have a star-forming disk. How much star formation is there?
Yes.
With this, what I did and the team did is we went back to radio observations by Song et al. And others
Okay.
and looked at how much of the flux was not in the core. We did this by comparing observations obtained at high resolution and low resolution. And we found that there was something like 10, 20% of the radio flux was not in the core. And
Okay.
that gave you a star formation rate of something like, I forget the exact number, 7 solar masses a year or so.
Okay.
Not a giant starburst and
Right.
not enough to power the galaxy.
Right.
Okay, and there's the sodium, and let's see. Um, all right.
20%.
So now the other thing that we did is we looked at
Yeah.
the stellar mass to light ratio of this galaxy,
Mm-hmm.
all the pieces together, and we discovered that with the con there, this galaxy produces an awful lot of light relative to its stellar mass.
Okay.
Luminosity is very high. It's higher than the starburst M82, which
Yeah.
again is just the hidden power source. So this brings us to the nucleus. All right, so let's go to the next diagram. Why is this diagram in the paper? Well, it's a paper about a con, only we can't see the con.
Can't see it.
Let's show why we can't see the con. That's what this is.
Okay.
It's in this bright ring, but the bright ring has a minimum near the con.
Yes.
So and also there's a hint that the dust lane extends below the con as well, before it is totally smeared out by the dusty material in the foreground. Can't be sure, but it looks like we have an outflow from the con here. And that's the interpretation, that's the prime interpretation here.
Okay.
So what we're seeing then is the con producing a basically kiloparsec scale outflow like this that's highly collimated and is shooting gas up into the outer atmosphere of this galaxy.
Okay.
Only it isn't simply extending out of the galaxy. Why? It has above it the polar ring.
Polar rings, yeah.
So this is a really messy interaction going on where stuff is going. What goes up may well come down in this galaxy because the polar ring is there. So the outflows remain collimated up to kiloparsec scale.
Right.
And those are flow times of something like a few million years for velocities of a few hundred kilometers a second.
Okay.
So these features are a few million years old, most likely. And they appear to be episodic. You can even see in that diagram slightly the clumps
Oh,
appearing.
yeah. Uh-huh.
So the thing goes puff, 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 possibly.
Oh, yeah. Boom, 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 boom.
Boom, boom, boom. And this is some work that's in progress now. I'll come back to that, trying to understand that. So we have a situation where the nucleus is tiny, it's a power source, and the way it appears to be influencing the galaxy that we can see and observe on large scales is by ejecting a flow of material up into the medium, which mixes and comes back down. Now, some of this, as particularly my colleague Suzanne Elto likes to point out, and also Mark Gorski did some work on this may resemble a protostar. This nucleus may be behaving a lot like a protostellar system with an outflow and material coming back in and a radial inflow with accretion as a pressure on the outside of the con. So this con may be being resupplied by gas flowing back in.
I love that analogy. It's great.
So it's a possibility that we're seeing a similar kind of system on a much larger scale. Like I said, Mark Gorski has a very nice paper that really leads a paper that outlines this.
Great.
So the nucleus may not have a fixed fuel supply. Okay, then here we go back to bring up the point about the minor merger may be a critical factor here.
Yes.
It may be supplying the low angular momentum gas. It also perturbed the galaxy. And we know that minor mergers can compactify a galaxy. So a galaxy with a disk already, if the merger comes in, this goes back to work in the 1970s and 80s, the material can go into the center, which is what we want.
Right.
Okay, so now we have the pieces. Now we have to discuss what's going on. And I will try and do this much more quickly than in the paper. Okay. So we have a dense gas disk. It's perturbed, it looks like, by an interaction. We don't know if there's a bar. Possibly there's a bar in the plane of the sky. We wouldn't see it then.
Okay.
So we don't know exactly how efficiently gas is being transferred from the disk into the center and by what processes. However, there is evidence in the molecular line data for an inflow, but that could also be an asymmetry associated with the past interaction. How long ago was the interaction? Well, it was long enough ago for the inner part of the galaxy to merge, which means probably tens of millions of years, 30 40, 50 million years.
Mm-hmm.
And not so long ago that the polar ring has gone away, well, that's a billion years, so that doesn't tell us too much. So it's an ongoing merger, late phase.
Good. Good.
So this can explain our galaxy. So why Zwicky 49 came out to be a con living in the middle of nowhere is it ate its friend, a very aggressive galaxy. Okay, let's go down here, and it would be a lower mass intruder because the disk is not highly disturbed.
Right. Minor merger.
Okay. The next thing is the central dusty obscuration is also vertically expanded. We don't know the kinematics of that material, except we did look at sodium in that direction. And again, along the minor axis, not in this paper, but it also shows no velocity gradient or very little. So it's possible the low angular momentum gas is hanging out in a turbulent medium over the center, which again can be a key factor in the system. Where did that turbulent medium come from? Well, dropping gas from a polar ring is a very good guess, but it's only guesses at this point. We just don't have the large-scale kinematics of that material. And it's not clear that the ionized gas is necessarily following the same kinematics as this denser gas it may be. In a polar ring, material can move through each other. So you have to be a little bit careful. Okay, the dust pillar outflows show, at least for pillar 1, that material is flowing out of the con. For pillar 2, we aren't quite sure what's going on. Pillar 2 and pillar 1 do not meet at the con. So one possibility is that there is a second outflow from the nucleus and it's bent, which we see, for example, in NGC 253 due to rotation. The other possibility is it's part of another feature altogether. The fact that it's dense and narrow suggests it's another collimated outflow. Well, if you really would like to be speculative, we ate another galaxy. Small galaxies sometimes have nuclei. Perhaps there's a second accreting nucleus in there as well.
Ooh,
Also,
yes, 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 yes.
that would explain the inflow. That would drive it. So this could be a double nucleus galaxy, but we have not detected the other nucleus.
Okay.
But there's a sort of a dotted bat single finger pointing in that direction, but it's not there yet.
Mm-hmm.
Okay, so now what do we have to say about the nucleus itself? It's hidden. So the first thing we can say is we don't see it. Okay,
Yeah.
that's probably where we should stop, but no. We know a little bit more about the system. We know that it has a very high infrared luminosity.
Yes.
The nucleus is powering it, and that the nucleus is losing gas on basically a multi-mega-year timescale at something like a few solar masses a year, 1 to 10 solar masses a year.
Wow.
We also know the nucleus contains order 10 to the 8th solar masses. So one of the interesting things is if nothing else happened, but just the mass loss and it didn't come back, 10 to the 7th years and you're out.
Ooh, gone. Okay.
The other thing we can see is those little puffs are about 100,000 years apart.
Mm-hmm.
The nucleus is only 30 parsecs across. The time scales are very short. So we're looking at a very rapidly evolving system. That's what we've learned from the system, from the study. Even though it's rapidly evolving, this nucleus is able to considerably influence a region of at least several kiloparsecs over the central scale of the galaxy.
Yeah.
So
Nice.
sort of major point about all of this, there is feedback, it is happening, it's powered on a very small scale. Warning, this can happen in other galaxies, and there's a lot of gas around, and a lot of gas not necessarily in planes is where this is happening. A little yellow caution sign for doing high redshift research. You could really have some problems there.
Caution.
Okay, how about the central black hole? How is it being found?
What we got here?
Here there's a problem that is really independent of everything we've talked about so far, which is just all the dust around means radiation pressure is a problem. If you try to power the galaxy simply by ramping up the black hole, it ought to blow everything away. It hasn't. So what's going on? Either the black hole is too massive,
Okay.
radiation pressure, so you want to have the black hole running at a low Eddington factor, a low power output relative to its mass. So one possibility is that the black hole is really massive, and that's why this became a con, because it could collect all this stuff in the center without blowing it away. A lot of mass.
Okay.
Another possibility is radiation is tricky. It goes out through holes.
Yeah, Swiss cheese through there.
Swiss cheese through there. And once it goes out through holes, the pressure drops. This is a known source of flat tires, for example. A little hole does the whole thing. So you can actually perhaps deflate the radiation pressure by leaking out of holes. But notice we don't see any bright shafts of light.
Yeah.
in our HST image. So that does not look terribly good,
Okay.
but maybe we could sneak it in the infrared. Perhaps James Webb will tell us something about that.
Okay.
So if the black hole is very massive, then the Kahn phase does very little to grow the mass of the black hole. If
Mhm.
the black hole is normal mass, which would be below 10 to the seventh or around that matter, then it's accreting at near Eddington, and
Yes.
the black hole is growing very rapidly. And the Kahn phase is a phase of black hole growth, and
Yes.
we don't know for sure, but probably also star formation growth.
Goes.
Okay,
Cool.
so
Cool.
now we come to the confirmation, and this is the problem of how you collect this gas. And basically, the point here is minor mergers seem to be a way of doing this.
Yeah.
Other cons, NGC 4418 and IC 860, share with SPICY 49 being
Yep.
involved in minor interactions.
The classic.
However, there's a galaxy, another con, which is not necessarily in an interaction. So it's not a one-to-one thing, but at least that's one channel that works.
Yeah.
So it may well be that the other channels involve a situation where large amounts of gas get put into the center rapidly. So the hints there are a disturbed galaxy and rapid gas inflows and non-circular waves are driving these cons.
Okay.
All right, I think we can go down towards the end here.
Okay. Boop, 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 boop. I'm with you.
Did we ever get to a conclusion? Yes, we did. Oh yeah,
We
time
did.
scales are short.
Yes.
Okay, so why study this galaxy in detail? Why write a supplement about one galaxy? Because it's a rare type of galaxy,
Yes.
but it is rare in the current universe because it's unusual for a galaxy to accrete a lot of low angular momentum gas.
Mhm.
Cons are important because they tell us about situations where low specific angular momentum gas gets into the centers of galaxies. We've known this in ULERGs. This goes back to Gao and Solomon, how interactions do this. ARP 220 does this.
Yes.
But we don't understand the general behavior of these very dense systems, so we need to study the few nearby examples in detail and in multi-wavelength ways, which is what this study is part of. And the
Mhm.
Conquest team is continuing to work on this in different ways. For example, the upcoming Muse paper and all the recently published LANCAR molecular line paper.
Right.
Okay, and so that's the bottom line on these things. I think they're extremely interesting, not as rare birds, but as rare birds tell you something about the evolution of birds in general.
Indeed. Very cool. Beautiful, 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 beautiful.
Okay,
Jay, that was awesome. I want to thank you so much for walking us through your very awesome APJ sub article.
thank you. It's a
Yeah,
pleasure.
very good.
Hope people enjoy it.
Oh yeah,
Feel free to skim
I
it.
did. So you kind of touched on it a little bit there. Actually at several points. So let me go ahead and push on it a little bit. And where do you think we go from here, given the published article? So are there
Okay, I
still
think there are
more
multiple
with to
things.
do?
Yeah, where to go? First of all, enlarge the sample of cons. You have to go out further.
Okay.
Secondly, we've been focusing on lurgs and ULERGs, but there's con-like behavior in galaxies that are less massive. For example, if the con behavior is a matter of ratio of gas mass to nucleus mass,
Mm-hmm.
lower mass versions of cons may exist. They may be nearby. They may tell us more about the processes.
Cool.
Third, we need to really get at these time scales.
Mm-hmm.
How fast, how rapidly are they evolving? So ongoing work on that is proceeding with the con team, with various people working on different things. Another major area is how do cons connect to other kinds of obscured nuclei? For example, George Priven's done a lot of work on that.
Okay.
I have an undergraduate at Macalester College looking into how do cons statistically compare with populations of Compton-thick AGN.
Yeah. Yeah.
Are they a different evolutionary phase, or are they a distinct population? If they're distinct, what the heck do they relate to?
Yeah.
That's an issue, trying to put them into the evolutionary flow. And then I think the other part that's just opening up now is with all of the molecular line data, with more information about the surroundings, we can now start to make the kinds of detailed feedback numerical models. These cons are so complex. I'm in the process of made a back of the envelope star formation model for a con.
Yeah.
What I discovered is almost instantly all the massive stars you have to put into it make H2 regions. H2 regions push the gas together. So my uniform sphere
Oof.
immediately turns into Swiss cheese with very dense regions,
Yes.
and with radiation pressure pushing this stuff at maybe 50, 60 kilometers a second into a turbulent mess. So it tells you it's unstable. It tells you you have to go after this numerically. So getting the numerical experiments and knowing the initial conditions is going to be extremely interesting. Then if there is star formation, there's a good chance it's really weird and is perhaps associated with making primarily massive stars. So we ought to think about how we would figure that out.
Yeah.
The ionized gas is one way, X-ray binaries is another, but this is really in the, let's look at it. Future, obviously James Webb is going to tell us some things. Beyond that, I think higher resolution VLBI observations in the millimeter are going to be very important.
Okay.
And back to the bottom line of cons in general, remember, just because it's small doesn't mean it isn't powerful.
Awesome. Awesome. Well, it's going to be really exciting to see this develop over the next couple of years.
Well, thank you. Yeah, it's
Observations
interesting.
coming in. And it's a complicated enough system where you need all these diagnostics to get in there.
Yep.
It's very cool.
And I think the answer, we shouldn't be put off. I think we can understand these, and they can tell us a lot about how galaxies actually operate as baryonic processing machines.
Very nice. Cool. Jay, thank you so much once again for walking us through your very life.
Thank you. Thank you.
Yep. And that will do, everyone. And I hope this made your Galaxy Astronomy Day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.